Hello friends, in this video I am going to explain or I am going to give an overview rather of an AVL tree, which is a type of a binary search tree having some special characteristics associated with it. So AVL tree is a very important tree in the data structures, in the study of data structures, and we are going to have a session in this video in which I am going to give an overview of an AVL tree. What is an AVL tree and what are the characteristics of an AVL tree, how binary search trees can be considered to be an AVL tree, and so on. So AVL tree is nothing but I can say it's a binary tree. It can be a binary search tree. So in the way I'm saying that if it is a binary tree, an AVL tree can be a binary tree. If an empty binary tree can be considered to be a binary tree, then an empty binary tree can also be considered to be an AVL tree as well. And AVL tree has a special characteristic in that there is a balance factor which is associated with an AVL tree. An AVL tree means if a binary tree is an empty binary tree, then it can be considered to be an AVL tree, but if it is a non-empty binary tree, then there is a balance factor which is associated with the concept of the AVL tree. What is the balance factor? For that I will just assume it that the binary tree containing a left subtree and a right subtree, of which the height of the left subtree can be called as assumed to be HTL, or that is the height of the left subtree, and the height of the right subtree is the HTR. And when this HTL minus HTR, that is the modulus or the magnitude of the difference between the heights of the left subtrees and the right subtrees, gives a result of 0 and 1, and the result always just lies between 0 and 1 and not less than that and not more than that. So if it is, suppose if I assume it to be HTL as the height of the left subtree and HTR as the height of the right subtree, I'm just trying to explain it in this mathematical formulation, that is height of HTL, height of TL minus height of TR. This is the modulus operation. It is placed between a pair of pipes, and that means a modulus operation, that is the magnitude of the difference between the HTL minus HTR will always be less than or equal to 1. So it will not be and it will start from 0 and it will be 1 maximum and not more than 1. So we can say like this, it will be like this. So this 0, it can be 0 or it can be more than 0, and always this is going to be maximum, it will be going to be equal to 1. So this value, this modulus value, that is the magnitude of this difference operation, gives you only two possible values, that is 0 and 1. So if we just take it in another form, that is if we just deal with the sign and not the magnitude, then the possible values of the balance factor can be like this. Suppose HTL can be, HTL minus HTR can be 0, or HTL minus HTR can be 1, HTL minus HTR can be minus 1. So the value will be just varying from this 0, 1 and minus 1 and lie within these three values. So, and balance factor is nothing but, this is a balance factor. So balance factor is nothing but the height of the left subtree minus the height of the right subtree. So balance factor, I will write the full form as well, balance factor. This is the most important part to be considered in an AVL tree. For a binary tree to become an AVL tree, the balance factor should have the formula of like this, and having a value either 0 or 1 or minus 1. That is, if we just sum it up in terms of this modulus operation, that is the magnitude of the difference between the left subtree, height of the left subtrees and the right subtrees, we will get the relation like this. So this HTL minus HTR, modulus of HTL minus HTR is greater than or equal to 0, that it can be 0, and it can be, ultimately it can be, maximum it can be 1, because it is less than or equal to 1. So there is no possibility of it being less than 0 or more than 1. So this is the concept, this is the overview of the AVL tree. So suppose if we just consider this tree, if we just consider this tree like this, suppose this is a tree, suppose this is a tree. So this tree can be easily seen to be that it looks like a binary tree. It is a binary tree definitely, because the binary tree characteristics of binary tree, as you all know, that the binary tree contains at most 2 child nodes for each of the node present in the binary tree. So this node has 2 children, this node has 1 child, this node has no child, this node has no child, and so on. So this is definitely a binary tree. But let me see whether this binary tree satisfies the condition of the AVL tree, that is the balance factor lies between these 3 values. Let me just check. Suppose it can contain any values, it can contain any values. So value is not a thing to matter in this part. So we'll just see the heights. Suppose this, if we consider this node, then there is the root node, then the left subtree is this one and the right subtree is this one. The height of the left subtree is nothing but 1, 2. So HTL comes to be here 1. Sorry, HTL comes to be 2, 1, 2. Then the height of the right subtree is only 1, that is 1. So if we just see that what is the height difference or the difference between the HTL and HTR, for this we see that the HTL is 2, HTR is 1. So 2 minus 1 will give you a value of 1. So the balance factor of this root node becomes 1. Let us see this node, let us consider this node and see what is the balance factor. What is the HTL over here? HTL is 0. HTL is, because there is no child, the HTL is all definitely 0, and this HTR is 1 because it has only 1 child in the right subtree, only 1 node in the right subtree rather. So this will give you a balance factor of 0 minus 1, that is minus 1. So we will write these balance factors alongside these nodes in parenthesis, and we'll see whether all the balance factor of the tree of the tree which I have drawn on this board matches with all these with these possible values which should be there, which should be in place in order to conclude that this binary tree is nothing but an AVL tree. So let me see this one. There is no left subtree, there is no right subtree. There is the balance factor of the balance factor comes to be 0 because HTL is 0, HTR is also 0, HTL minus HTR is 0. So this balance factor is 0. Let us put it in parenthesis. For this, a similar concept to this one will also apply over here, because there is no left subtree, there is no right subtree. So the balance factor is definitely HTL minus HTL is HTL minus HTR is equal to 0 minus 0. That will give us a value of 0. So we see that for these all 4 nodes which make up this binary tree, we can see that all the balance factor associated with each of the nodes of this binary tree are having balance factor values of 1, 0, 0, minus 1, which are nothing but very much in conformity with the permissible values of a binary tree to become an AVL tree. So in this case, we can conclude, in this situation, we can conclude that this binary tree which I have drawn on this board is definitely a binary tree. It is definitely a binary tree, but this is an AVL tree as well, because all the balance factor values are in conformity with the expected values for an AVL tree. So this is the concept, this is a brief concept of the AVL tree, and there is one more concept which I want to share in this video, that is AVL tree can be also considered to be AVL search trees. In that case, for binary trees to be an AVL tree, we will consider an analogy to that situation, that a binary search tree can become an AVL search tree. So when the binary search tree can be an AVL search tree, and a binary search tree, as you know, that it is partitioned into in this way, that is, suppose this is a binary search tree. Suppose this is a binary search tree, the values will be like this. Suppose this is 10, this is 5, this is 15, this is 12. So this is a binary search tree, as you all know, because binary search tree are partitioned in a manner that always the root node of any subtree of the binary search tree will have some value which will be greater than the all the values on the left subtree, and which will be less than all the values of the right subtree. So this is definitely a binary search tree which we can see on the board. But let's see whether this binary search tree can be considered to be an AVL search tree, because in order for a binary search tree to become an AVL search tree, the conditions which have been discussed before should definitely hold. So let me see whether the balance factor for all these nodes are in conformity with these three values. If they are in conformity with these three values, then we can easily consider this binary search tree to be an AVL search tree. So let us see the balance factor for this node. Suppose this is a height, left subtree has a height of 1, right subtree has a height of 2. So 1 minus 2 will give you a balance factor of -1. This has no left and right subtrees, so the difference between the height of the left subtrees and right subtrees will give you a value of 0. This has a height of the left subtree as 1 and there is no right subtree, so the difference between the heights of the left subtrees and right subtrees will yield the difference, will yield the value of 1 minus 0, that is 1, and for this the balance factor will definitely become 0, because there are no left subtrees or right subtrees for this node having the value of 12. So this will have a balance factor of 0. So see, all the balance factors for each of the nodes associated with this binary search tree are in close conformity, to these values, that is 0, -1, 1, 0, that they are not any other values than other than these three values. So this binary search tree is definitely a binary search tree, but at the same time it can be considered to be an AVL search tree as well. So AVL search tree. So one point which I should have mentioned before, I will just give it a mention now. Sorry for not mentioning it before, because AVL tree is named after the three great men who had discovered this concept in these data structures. AVL tree is an acronym for the names of the three great men who has discovered this AVL tree, that is Adelson, Velsky and Landis tree. So this AVL means AVL stands for, A stands for Adelson, V stands for Velsky or Velsky, and L stands for Landis. So Landis. So this Adelson, Velsky and Landis are the three scientists who discovered the concept of the AVL tree. So the name comes from the initial letter of each of the scientists' names, that is AVL tree. So this is a very important tree to be considered as a part of the study of the as a part of the discourse of data structure. So if you have any doubts or queries relating to this entire overview of AVL tree and AVL search tree which I have given in this video, you can well post your doubts and queries in the comment section below so that I can address them. Thanks for watching this video.